Earlier in this topic, we talked a lot about temperature and how the temperature is a measure of the internal kinetic energy of an object. We also defined heat as energy on the move, and in this lecture we will link these two concepts. So far we've talked just about a single substance, but how about if we wanted to understand what happens when you heat another substance like gold, for instance? How much heat energy will we need? How do we think about this problem? Okay, let's start with our intuitive knowledge of the general situation. We want to know how much heat we need to raise the temperature of a body of gold. The amount of heat Q we need must be proportional to the mass of the body M. We would clearly need more heat to raise the temperature of 200 grams of gold compared to 100 grams. So we can write that heat Q is proportional to mass M. Remember, this little alpha symbol means proportional to. We will clearly need more heat if we heat up our gold by 50 degrees compared to, say, 5 degrees. So heat must also be proportional to the change in temperature, delta T, where the Greek symbol delta means difference or change in. So now we've got the heat is proportional to the mass, delta T. Now we want to make this expression universal to all material. We're going to lose the proportionality sign and just add an equal, because the variable C, called specific heat, is the proportionality constant. Specific heat is a material's specific property, which must be measured via experiment. Thus we have the final expression of heat equals specific heat times mass delta T. Q equals Cm delta T. So what are the units? Let's do a quick dimensional analysis to find out. We write Q equals Cm delta T and rearrange to get C equals Q over M delta T. Now we replace the variables with units. Q, heat, has the units of joules, mass, M, kilograms, and delta T, temperature, in Kelvin. So then we can see that the units of specific heat C are joules per kilogram Kelvin. Here's a table of some specific heats. You'll notice that water has a very high specific heat compared to a lot of other materials, including gold. What this tells us is that we need more heat to raise the temperature of a mass of water than we do for the same mass of gold. The human body is made up of waters, proteins, fats, and minerals. To an approximation, this is 75% water and 25% protein, approximately. So we could calculate the specific heat capacity for a human body based on a simple rule of mixture. If we say 75% of the specific heat of water, 4186, plus 25% of the specific heat of protein, 1680. We multiply that out, we get the specific heat of a human body, which is approximately 3,560 joules per kilogram Kelvin. Specific heat is an interesting idea. It can help us understand the concepts of internal energy, temperature, and heat. If we think of a mass of water at 50 degrees C and a mass of gold at 50 degrees C, we know now that we would have needed to add much more heat to the water to achieve this temperature than for the gold, as the specific heat of water is greater than the specific heat of gold. But why? And where does this extra energy go? Looking at this schematic representation of the internal energies U of water and gold, we can start to understand. Remember that internal energy equals the sum of the kinetic energy and the potential energy. Let's look at the kinetic energy component of the water and the kinetic energy component of the gold. You will notice that they are the same. This makes perfect sense as the two substances are defined to be at the same temperature. Now let's look at the potential energy component of the water and the potential energy component of the gold. This time they're not the same. You will notice that the potential energy of the water is very much larger than the potential energy of the gold. So we can now visualize that we would need to add a lot more energy to raise the potential energy proportion of the internal energy in the case of water compared to that of gold. Therefore, the total energy required to heat the water is greater than the energy required to heat the gold.